Well, in lecture A, at the end of lecture A, we were talking about sequences and direct formulas. We considered an example here that appeared to be approaching 0. A student named Gabriel here brought up, I'm wondering if there's an algebraic way of connecting this formula with a simpler formula here, because they were the same sequence. And yes, there is. You can, for example, factor out -1. You can call it the n power, or even the n plus first power out of the top. And what you're left with up top is 3 times -1 to the n minus 1 plus 4 times 1 over n. And this simplifies. Oops, this is a mistake here. Sorry, this is just a -1 power. This is -3 here, and this is 4. So this whole thing simplifies to 1. So we really end up getting -1 to the n plus 1 times 1 over n, which is the same thing as this. So they were the same formula, and they do produce the same sequence. Then we talked at the very end of lecture A, can we prove this sequence converges to 0? It does seem like the limit should be 0. That seems pretty clear. You can look at both the numbers themselves and the formula, and you know, you're dividing a number that's either 1 or -1 by a number that keeps getting bigger and bigger. Why shouldn't it converge to 0? Well, to prove it converges to 0, you need to show that the distance between Sn and L, this is the distance between them, can be made as small as we like by taking n sufficiently large. How do you verify that? Well, you work with this expression, the distance between Sn and L, and you try to simplify it as much as possible. In this case, it simplifies pretty nicely. Sn is, once again, -1 to the n plus 1 over n. L is 0. When you subtract 0, that doesn't affect things. The absolute value of a quotient is the quotient of the absolute value, so I can write this. -1 to a positive integer power is either 1 or -1. Its absolute value, no matter what, is 1. And n is a positive integer. Its absolute value is itself. So this distance between -1 to the n plus 1 over n and 0 simplifies to 1 over n. Can you make this as small as you like? Sure. Can I make it smaller than 0.1, for example? Yep. Make n bigger than 10. 1 over n will be less than 0.1 if and only if n is bigger than 10. Can I make it less than 0.01? Sure, as long as n is bigger than 100. Can I make it less than 1 over a Google? The number Google, not the search engine. The number Google came first. It's spelled differently, by the way. You can look it up. Can I make it less than 10 to the -100 power? Sure. Make n bigger than a Google. That's equivalent to n being bigger than a Google. 10 to the positive 100 power. By the way, a Google is an unimaginably large number. It is bigger than the number of atoms in the known universe. A Google. I'm serious. At least according to what I've read. The number of atoms in the known universe is on the order of 10 to the 80th something. Maybe 81st or 82nd power, I'm not sure. A Google is trillions of times bigger than that. Trillions of times more than the number of atoms in the universe. Is how big that is. Okay? We can get even more extreme. In general, we can say that 1 over n is less than any positive number, call it epsilon, if and only if n is bigger than 1 over epsilon. Epsilon is a Greek letter. It's a common letter to use as a measure of smallness, of arbitrary smallness. It's not the only letter that can be used. It's just a common letter that people use. So by saying 1 over n is less than epsilon, in treating epsilon as an arbitrary positive number that could be very, very small. By taking n bigger than its reciprocal, that's how big n needs to be to make sure 1 over n is smaller than that. That's how big n needs to be to make this distance less than epsilon, where epsilon is an arbitrary positive number. This is not a proof that I did here, because I didn't write an argument out in sentences. I described the idea of the argument. For the sake of time, we're not going to do a full proof here today, because we have other things to do. Maybe we'll do a full proof on Friday of some other example. Will you have to do full proofs? Possibly. Or if you did, I'd give you some guidance, I think, on the test, so that you don't get too bogged down in the details. Okay? But we want to understand the basic idea. Sequences, as we've seen, can also be defined by indirect formulas, more commonly called recursive formulas. Recursive or indirect formulas. They have other names. They're sometimes also called difference equations, for reasons I won't get into. You've got some starting value for your sequence, so you can pick it to be anything you want. -3, for example, might be your starting value. And then you've got some equation. Well, the book typically gives the nth value of the sequence in terms of the previous values, the n minus first and n minus seconds. But I wrote the n plus first value in terms of the nth value. And for example, I could do Sn squared. That would be equivalent to writing Sn equals Sn minus 1 squared. Although the range of values for n that you think about would be slightly different. Here you don't use this equation when n is greater than or equal to 1. Here you use the equation when n is greater than or equal to 2. This one is for n greater than or equal to 1. This equation defines the same sequence with the same starting value when you use n greater than or equal to 2 for this equation. They're the same idea. The next value of the sequence is the square of the preceding value. That's what it is. So if you wanted to figure out the other values in the sequence, S2 is S1 squared, so that's -3 squared. +9. S3 is S2 squared. 9 squared, +81. The numbers are going to be positive from now on, and they're going to get big really fast. S4 is S3 squared, +81 squared, which is whatever. 6,000 something. And then I take that 6,000 something and square it to get the next number. 6,000 squared is, what, 36 million? I get somewhere in the ballpark of 40 million. I'd have to square that number and get, what, somewhere in the trillions, I guess? Question?
Does it for it to be recursive, does it necessarily have to have something involving the previous?
It could involve the 2 previous values, or maybe...
Or just something with n, like you did on us?
That would be more of a direct formula, if it just involves n and not a previous value. This sequence seems to be diverging. Yeah, it is diverging. Though it is diverging in a special way, the numbers keep getting arbitrarily large positively. You might say it's diverging to +infinity. I'm not going to prove that, but that should seem pretty clear. You can graph sequences, as I mentioned last time. The one that's -1 to the n plus 1 over n can be graphed as follows. When n is 1, it is 1, so it's up here. When n is 2, it's negative 1/2, so it's right there. When n is 3, it's positive 1/3, then negative 1/4, then positive 1/5, etc. It's going to keep bouncing back and forth above and below the axis, and continue getting closer and closer to the axis as n increases. Technically speaking, you should not connect the dots, though some people do anyway. If you did connect the dots, they'd go down, up, down, up, down, up, down, up. And you can also graph sequences just on pure number lines. One is the first value, that's S1. Then you jump over to 1/2. I'm drawing negative 1/2. I'm drawing arrows, but it's not typical to draw arrows. Then you jump over to positive 1/3. Then back to negative 1/4. That's 4. Back and forth. It's like a bunny hopping back and forth. Does the bunny go in the hole? Is there a hole? Well, there's not really a hole. You might say, well, the limit is 0, so should 0 be the hole? The terms in the sequence never actually equal 0. Suppose if I'm doing a bunny jumping, I should do this kind of thing. Okay. I didn't mean to do it, but I accidentally went like this. It was subconscious. Okay, it's not that the bunny ever gets in the hole, but it gets closer and closer to the hole, arbitrarily close to the hole. This bunny is never satisfied, though it never gets in the hole. But how can there be a hole at one point anyway? Okay, don't take the hole analogy too far. Okay? So you can graph it in a couple different ways as well. Recursive formulas, I think I should mention, can generate some pretty interesting behavior. If you want to get Mathematica to generate recursively defined sequences, turns out there are good ways of doing it and bad ways of doing it. The bad ways get bogged down too slow. The best way, at least when your sequence term depends on just the preceding sequence term, is to use a function to do the iteration for you. What do I mean by that? Well, if, like with this example, if I let f of x equal x squared, then this equation right here is equivalent in this situation to Sn plus 1 equaling f of Sn. I can use the function x squared to do my iteration. That's what, by the way, when you use a recursive formula over and over again, it's often called iteration. And turns out the best way to do that on Mathematica is not to go f of f of f of f of f of negative 3, though you could. That's in the quadrillions, right? 1.853 quadrillion after applying the x squared function 5 times. 1, 2, 3, 4, 5. You can do that, but it turns out to be better to use a built-in command called NestList. You plug the function name in for the first argument, the starting value in for the second, and the number of iterations for the last argument, separated by commas. There's S1. There's S2. Negative 3 squared is 9. There's S3, 81. 9 squared is 81. 81 squared is 6,561. 6,561 squared is this, 43 million and change. That squared is this thing, that was the 1.853 quadrillion. Square that, get this, etc. Is that 10 times? Dare I look at what it looks like when you do it 20 times? It even did it kind of fast. The last number on here has many, 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 many digits. That's not just one number there. These numbers are separated by commas. There's a comma, I think. I thought I saw one. Oh, there we go, yep. That's separating two numbers in this sequence. All right, let's do one where the numbers aren't quite so nasty. Same function, but this time let's plug in a number less than 1, well, between -1 and 1, like 0.99999, and do 20 iterations. Those aren't so bad to look at. Maybe they're converging. What are they converging to? Is it 0? Or is it possibly something non-zero? Oh boy, look at those negative exponents. I think we're converging to 0 here. Strange things can happen though. Even with, oh wow, underflow occurred in computation. Amazing. Even when your function is relatively simple. Here's my favorite strange example. 4x times 1 minus x. NestList f for a starting value. The starting value is sometimes called the seed. Oh, let's try 0.1 and let's do 100 iterations. So let's try to figure out the first iteration by hand. In other words, let's try to figure out S2 by hand. With this function here, the recursive formula would look like this. S2 would be 4 times S1 times 1 minus S1, 4 times 0.1 times 0.9. And what would that be? 0.36, is that right? I think so. 0.36, I put a 1 there to only do 1 iteration. Do 2 iterations. Oh, yeah, the list. Forgot the word list. So that tells me Nest does iteration as well, maybe just individual iterates. The next iteration gives you S3 to be 0.9216. All right, what about 10 iterations? 100. They're all between 0 and 1, but they're kind of all over the place. Weird. This is no mistake. This is the behavior of the sequence, and evidently it does not converge at all. But it stays between 0 and 1 all the time. Actually, this is not so strange. There are other ways of generating such a list. If you look at a table of values of, say, the sine function for integer inputs, you'll see similar erratic behavior. There are patterns in these things, but on a global level they seem kind of erratic. Only plugging in integer values there into the sign, nothing involving a rational multiple of pi. Still seems to be not converging, it seems to be diverging. So you can definitely have sequences that stay inside finite intervals, yet don't converge. -1 to the n is another example, bounces back and forth between 1 and -1 all the time. But if you have a sequence that stays in some finite interval, and it's monotone, meaning it's always going to the right or always going to the left on the number line, then it will have to converge. Here's an interesting example like that. I'm going to let Sn equal a certain summation. Is it doing that? K goes from 1 to n. I think I want to do 1 over k squared plus k. Turns out to be a summation where we can actually find a formula for Sn, a simpler formula without a summation. Let's just try to figure out the first few values anyway. S1 then is going to be the sum, k goes from 1 to 1 of that expression, which would be just one thing. 1 over 1 squared plus 1 is 1/2. S2 is going to be the sum k goes from 1 to 2 of an expression like this. 1 over 1 squared plus 1 plus 1 over 2 squared plus 2. That's when k is 1, this is when k is 2. 1/2 plus 1/6. Get a common denominator of 6. This will be 4/6 or 2/3. What's S3? 1 over 1 squared plus 1 plus 1 over 2 squared plus 2 plus 1 over 3 squared plus 3. 1/2 plus 1/6 plus 1/12. Getting a common denominator of 12 gives you 6/12 or 1/2. Did I make a mistake? Thank you. 9/12 or 3/4.
What was that again?
Maybe we're seeing a pattern here. It seems like Sn might be n divided by n plus 1. You see that pattern? That works when n is 1, 2, and 3. That formula works. Can Mathematica confirm it for us? Yep, I think so. Notice I pressed the summation button here. We've done that before with Riemann sums. K equals 1 to n of 1 over k squared plus k. I think Mathematica will return n over n plus 1. Yep. Our conjecture is correct. Is that difficult to prove without Mathematica? It's not too difficult, though it does involve a trick. You have to realize that 1 over k squared plus k is 1 over k times k plus 1. And if you use partial fractions, you can write it like that for sum a and b. Let's see if I can do it in my head here. A would end up being equal to 1, and b would end up being equal to negative 1 to make this work. Let me just check this in my head and see if this works. If you got a common denominator, if you went backwards and got that as a common denominator, you get a k plus 1 up top there and a minus k there, and the k's would cancel, leaving you with 1 up top. This does work. And so it can be plugged in here in place of that. And when you do that, what you end up realizing is that a bunch of stuff will cancel. I suppose it's worth writing down. Make that replacement. The summation, when you do that, looks like this. When k is 1, you get 1 over 1 minus 1/2. When k is 2, you get 1/2 minus 1/3. When k is 3, you get 1/3 minus 1/4. When k is 4, you get 1/4 minus 1/5, etc. The last two terms will be when k, first of all, is n minus 1, which will look like this. And then when k is n, it looks like this. And everything cancels except the 1 and the minus 1 over n. The negative 1/2 cancels with that 1/2. The negative 1/3 cancels with that 1/3. The negative 1/4 cancels with that 1/4, etc. The only two things that don't cancel are that and that. This equals 1 minus 1 over n plus 1, and getting a common denominator of n plus 1 helps you see this is n over n plus 1. And that is a quantity that as n goes to infinity converges to 1. This sequence of these s's, 1/2, then 2/3, then 3/4, then 4/5, then 5/6, that converges to 1. The sequence does converge. And because we're defining the sequence with the summation, it's tempting to say, I wonder if I can do a summation where the top thing on top of the summation is an infinity. And the answer is, you can. And the answer is 1. Oh! Need a K there. 1. In our last 6-7 minutes here, let's go back to geometric series and realize finite geometric series really generate sequences, those formulas. In a similar way as this example. Well, that is not a geometric series. Take an example. This is the simplest geometric series that is at the same time significant that I know. Really, that's kind of funny to say. It's the simplest. They're all sort of equally simple. This is a first example many people often consider. Adding 1 over powers of 2, including the first one, by the way, which could be thought of as 1 over 1. And the one on the bottom could be thought of as 2 to the 0 power. If I have a finite geometric series with n terms in this situation, the last term would look like this. The a is the first term, that would be 1, and the x, the common ratio, would be 1/2. Remember we saw last week, I'm not re-deriving it for people in the video who watched last week's videos. That's today's lecture 22, I think, so like lectures 18 and 19. To see that the answer is a times 1 minus x to the n over 1 minus x. In this case, that's 1 times 1 minus 1/2 to the n over 1 minus 1/2. Dividing by the half, a half is the same as multiplying by 2, so this can be written like this. 1/2 to the n is the same as 2 to the negative n. You can leave it like that. You can also bring the 2 inside if you like and write it like this. This geometric series, this finite geometric series, for any positive integer value of n, equals this. And that can be thought of as a direct formula for a sequence. And it's a sequence that converges as n goes to infinity, because this goes to 0 as n goes to infinity. You have 2 to a power that keeps getting more and more negative. The negative power grows without bound, and that makes this go to 0. So Sn itself converges to 2 as n goes to infinity. The finite geometric series generates a sequence that converges to 2 in this case. And therefore we say the corresponding infinite geometric series converges to 2. We say this sum right here, where the summation goes on forever and ever, that equals 2. what that corresponding sequence converges to. How can you add up infinitely many things, though? You actually can't add up infinitely many things. Nobody can. But this corresponding sequence of the sum of finitely many terms does converge to 2, and so because of that, you say it makes sense to say the infinite sum converges to 2. Even though you can't literally add up infinitely many things. Nobody can. If you put it into Mathematica, Mathematica will say the answer is 2. I can put an infinity up there. Zoom in on that if you need to. You can write this sequence, this series, as the summation k goes from 1 to infinity of 2 to the k minus negative k plus 1 power, actually. We'll do it. That'll be the infinite geometric series, and this does equal 2. But we're not literally adding up infinitely many things here, and that's kind of another funny thing in calculus where you're pretending like you're doing something, but you're really not. But it does make sense in many circumstances to pretend we're adding up infinitely many things. In general, this will be the last thing I say today. In general, that expression, as long as x is strictly between -1 and 1, will converge. This converges to a over 1 minus x if x is strictly between -1 and 1, because in that case x to the n goes to 0 as n goes to infinity when x is strictly between -1 and 1. And that's the formula in general for the sum of an infinite geometric series with starting or leading term a and common ratio x. You should know this for your homework assignment as well. Okay? So Wednesday's advising day. We'll see you on Friday.